Hi everyone, welcome to Module 4C for Kines 7103, which is taught in Health Kinesiology and Recreation here at the University of Utah. Today we're going to be talking about how we estimate statistical power using the proportional reduction in error and the F distribution. And we really want to address this idea of how can we design a study well, taking into consideration the chance of a false positive error and the chance of a false negative error. So as you were reading through the chapter, you've encountered this discussion of statistical decisions and the different types of errors that we might have. So in general, we're talking about making a comparison between some sort of compact model, for instance, a model where we just estimate one constant for everyone, right? So an unconditional model, against a model in which we might be estimating something more complicated, an augmented model, in which we're making a conditional prediction. So for instance, if this y is weight, we might be making an estimate of your weight based on your height, and by comparing between the two models, we can make a decision, do we think that weight is associated with height, or do we think these things are not associated with each other? Or I should say, do we think weight is associated with height, or do we not have evidence to conclude that they are associated with each other? So in that situation, we're making a decision about the null hypothesis, or really about what to do with model C, right? Because model C is the null model, and that is because in model C, right, the implied value of beta 1 is 0. So we're saying, is beta 1 0, or should beta 1 take on some other value? And when we make this statistical decision, we can either reject model C, we can say, okay, what we observed is unlikely to have arisen under the null model, or we can not reject model C, because what we observed might have very easily arisen under the null model. And that is ultimately going to align with some sort of true state of nature, right? Model C might ultimately be proven to be correct, or it might ultimately be proven to incorrect. And by crossing our statistical decision with the true state of the system, we arrive at this 2x2 contingency table. On one diagonal, we have accurate decisions, right? If model C was correct and we concluded not to reject it, that would be what we call a true negative. We accurately did not jump at saying, that there was an effect there when there wasn't. So for instance, if we were looking maybe at your relationship between height and IQ, height and IQ probably aren't actually related in nature, so model C would be correct. If we did not conclude to reject, then we would have made a true negative decision. The sort of reverse of that would be making a true positive decision, where, for instance, in the height and weight example, those things are related in nature. So hopefully in our sample, when we compared the model C to model A and we calculated an observed F value, if that F observed value was greater than the critical value, we'd make a true positive decision. We'd say, yes, we think these things are associated, and we would reject the null model. On the reverse diagonal, we have two types of errors, right? We have false positive errors and false negative errors. A false positive error occurs when model C is correct, but we conclude to reject it, right? So in the situation where we're looking at the association between height and intelligence, these things aren't related out in nature, but maybe in our sample, due to variability, right, they happened to show a strong positive association, and we thought we had evidence that taller people were also smarter, right? Subsequent research might ultimately prove us wrong, and therefore we made a false positive. We concluded that there was an effect there when in reality there wasn't. Conversely, right, if we come down to this side of the diagonal, we can also make a false negative error. So this is what we might call a miss, right? So if there is a real effect in nature, but we miss it in our sample. So in the height and weight relationship, those things are true, right? Those are truly related in nature, but maybe in our sample, we didn't actually see a strong enough relationship between height and weight to reject model C. So we didn't reject model C when in fact we should have, meaning we missed an effect that was there, or we made a false negative. Okay, so what we want to do is think about how can we design studies in which we control the chances of our false positives and false negatives to make sure that if an effect truly is there, we're able to detect it. But we're also not just constantly saying everything's an effect. So we're trying to control our false positive rate as well. So the false positive rate is something that we've already talked about in the context of it's the alpha threshold for decision making, right? And we said that in our null distribution, we're going to draw some line at the alpha level Beyond that point, we might consider an effect statistically interesting because it's unlikely to have arisen under the null distribution, right? And everything below that point, we consider, well, this probably just arose due to sampling variability under the null, right? So in our previous examples, we talked about the F distribution for 1 and 9 degrees of freedom when there is no effect in the population, and that would look something like this. Okay, so this is what we would expect in terms of the F observed that we would get in a given experiment, and this is the proportion or the probability of getting that F observed, right? So in experiments when there isn't really anything going on, there's no effect to be detected, if we have 1 and 9 degrees of freedom, it's not going to be unusual to see F values below 1, below 2, below 3, until we start to get out to about 5, right? And in this case, if our alpha is set at 5%, the actual critical F value that corresponds to that is 5.12. So that means that 5% of this distribution is to the right of this cutoff, 95% of this distribution, right, if you look at the area under the curve, is to the left of this cutoff. So if we had an alpha of 5%, any F observed greater than 5.12 we would say is unlikely to have occurred due to under the null distribution, due to sampling variability alone. We would think that that is statistically interesting. However, we could choose other values of alpha and therefore have other F critical values that we might want to use. So, if alpha is 0.05, the critical F value is 5.12, as illustrated by the red line here. However, if alpha is 0.01, right, we were going to have a 1% chance, then the critical value is 10.56. So now that's going to be represented by the blue line drawn here. So you can see then, let's say we got an F observed value of 7, right, which would be somewhere in the middle of these two. Now, an F observed value of 7 is relatively unlikely, and you can contrast that against the probability, right, of getting that, assuming the pre is 0. So this is unlikely in the null distribution. But in one situation, an F of 7 is greater than the F critical value, and in another situation, an F of 7 is less than the F critical value. So an F observed value of 7, right, in one case might be statistically interesting if alpha was 0.05, but if we were being more conservative and setting alpha to 0.01, then an F of 7 we wouldn't consider statistically interesting because it hasn't crossed our conservative threshold yet. And we're trying to be very careful about controlling our false positives if we set the alpha to 0.01. So if F observed, right, is greater than F critical, that's a situation in which we would reject the null hypothesis because it is unlikely to have arisen from the null distribution. However, right, we get to determine what that rejection point is because we set alpha, which effectively sets F critical, right? And so if we set alpha to be lower and lower, that means we're going to be pushing it farther and farther along to the right of this distribution. And if we go to an extremely high level, if we set that alpha very, very low, right, we don't want any false positives. So that means we're going to need a really high burden of evidence in order to reject the null hypothesis. So we might think, well, why don't we just set alpha to be an extremely high value all the time to cut down on false positives? Well, the problem is if we do that, we're also going to get more false negatives. Because now, if I'm going to draw this very conservative threshold for alpha, maybe somewhere up here, and I get an F observed of 15, I would say, well, that's not statistically interesting. Well, now there's a very real chance that I've missed an effect that was there if I'm too conservative with what my alpha level is. Right? And the way you can think about this is if we swing this to either extreme. If I always say that an effect is there, right? So if my alpha level is 0, basically anything that happens, I will conclude there is an effect. Now, there's clearly going to be false positives there, right? Every time there truly is an effect, that's correct. I've made the correct decision because I said there was an effect when there was. But also, every time there was not an effect, right, I've also said that the effect was there. So if I set my alpha to 0 and I just always conclude an effect, every time an effect wasn't really there, that's a false positive. Conversely, if I shift my alpha all the way over the other way and I never conclude that there's an effect, basically I'm just never going to say that an effect is there, I will miss all the effects that were truly there. I'll never make a false positive because I never conclude that there is an effect, but for every situation in which there wasn't really an effect, in every situation in which there was really an effect, I will have missed it because I set such a ridiculously high bar for evidence, right? So the question is, how can we avoid false positive errors, but also reduce the chance of false negative errors when we're making these decisions from the data in our sample? So we can do this by taking a look at statistical power. And statistical power is the probability of rejecting the null hypothesis when a specific alternative hypothesis is assumed. Okay, so we know what the null distribution is going to look like, and we've done some work in previous lectures and in the labs to actually generate these distributions and say, okay, given that there's nothing going on, what do we think that the distribution of f would look like? And we can create a null f distribution. And then we can say at a certain point, value, an f observed greater than the f critical value, we think is unlikely to have arisen by that distribution. However, what we need to know is what are the chances of actually finding the effect that is there given what our decision threshold is. And in order to do that, we have to make some sort of estimate about what we think the effect is that we're studying. So we make an estimate about the true proportional reduction in error, or what the book refers to as eta squared. Right, and that's to separate it from the actual pre that we calculate, or the r squared that we calculate when we observe it in our sample. So this estimate should ideally be based on empirical data or some sort of clinically meaningful value, right? So I should be able to make some estimate of what I think the true effect size is based on studies that have been done before, or what the minimal important value is for my research question, right? If I change mortality outcomes by 1%, 1% might be really important for mortality, right? But for instance, if I change someone's hip circumference by 1% in a weight loss study, is 1% really meaningful, or is that a fluctuation we might expect due to chance? So these are hard to determine in some situations, and it comes from knowledge of your research domain, but you should be able to generate some realistic empirical estimate based on past work or minimally important differences that can inform your power calculation. Now, when all else fails, there are sort of rule of thumb effect sizes that can be used as a good starting point. In general, I don't think you should use these rule of thumb effect sizes, because I think you should know enough about your question to say, well, what kind of effects do I expect before I start studying it? But these rules of thumb can be handy if there is literally no other information available, or just as, sort of a useful starting point in building your power calculation. So for instance, the difference in mass between adult men and adult women in the United States is about 0.56 standard deviations. And by most of these rules of thumb guidelines, this is what we would consider a moderate effect size, right? It's a standardized difference of about 0.5 to 0.6. Now, what that looks like, if we plot this here, is we have a distribution of female weights, and we have a distribution of male weights. And you can see that there's significant overlap between these two distributions, but the mean of the distributions are about 0.56 standard deviations apart. In this case, I've standardized the distributions to make that a little more clear, so the females are getting centered on 0, and the males are centered on about 0.56. But you can see there's the mean of each of these distributions, and they overlap significantly, but their means are about 0.56 standard deviations apart. Now, if we were to translate this into a proportional reduction in error, it would have an eta squared of about 0.073, which is to say that if we were to estimate a model C, right, in which we estimate the grand mean for everybody and compare that to an augmented model in which we make conditional predictions based on your sex, right? So I make an estimate of the sum of squares for females, I make an estimate of the sum of squares for males, then I add those total sums of squares together. The proportional reduction in error from my conditional model is about 7% better than my unconditional model. So that doesn't actually sound that huge, but keep in mind that this is probably an intuitive relationship that if you asked anybody, we would say, yeah, males weigh more than females on average, right? There is significant overlap, but on average, most people would probably agree, just based on their informal observations of adult people in the United States or wherever you are, that males weigh more than females. Now, in order to determine the statistical power to detect this difference, right, we have to take into account what our false positive rate is, what our false negative rate is, and then we can determine the sample size we need to actually address this question. Okay, so one thing to point out here in terms of the notation, the false positive rate is written as alpha, so that's easy and that's something we've encountered before. The false negative rate, though, somewhat unfortunately, is written as beta, right? And so this isn't to be confused with the beta that we have in our regression model. We're using this due to historical standards, right? But this beta is the false negative rate, and I'll try to explain it in a little bit more detail in the image down below. Okay, but so if we want to know, all right, how many men and women do I need to sample in order to reliably conclude that men weigh more than women, right? Let's say that's my study, that's my hypothesis. Do men weigh more than women? Well, my null distribution, right? This is the proportion of F values and then we have the F observed value on the x-axis. And you can see that the proportion of a given F observed under the null hypothesis, right, goes down. And then at a certain point, we're going to cross our F critical value. So in this case, if we have 1 and 9 degrees of freedom, because we have, or sorry, this would be 1 and 19 degrees of freedom because it's 10 people per group, right? This is what that F null distribution would look like. And we're going to get a critical F value of 4.41, which separates the bottom 95% of this red distribution from the top 5% of this distribution. Right? Because alpha is set at 0.05, so the F critical value is going to separate the bottom 95% from the top 5%, which means that any F observed values we get greater than 4.41, we would consider statistically interesting, and we would reject the null hypothesis. So in order to calculate statistical power, we have to contrast that against our estimated alternative distribution, which in this case is shown as a dashed blue line. So if we assume the true eta squared is 0.073 and an n per group of equal to 10, this is the distribution of F observed that we would expect. And you can see that it looks slightly different, but in general, most of this distribution is still below our critical F value, which means if we assume this is the real effect and we're taking 10 people per group, we're still expecting to get an F observed lower than the F critical value most of the time. In fact, if you do the math here and calculate the proportion, the beta, right, or the proportion of this curve to the left of the F critical value is actually 78%, which means that we only have a statistical power, or 1 minus beta, of 22%, right? 22% of this dashed blue distribution is to the right of the F critical value, which means, assuming that this is the correct effect size, we would only have a 22% chance of concluding that men are statistically different from women in terms of their weight, right? So we don't really have enough people per group in order to reliably detect this rather obvious difference. So what if we increase the sample size? Well, now if we increase the n per group to 20, right, so we have 40 total people in this study, we have a different null distribution, right, because remember that the distribution of F is always going to change as a function of sample size. So even though the null always assumes no effect, the shape of it's going to change as the sample size changes. But you can see here's our null distribution. The F critical value is 4.098, which separates the bottom 95% of the red distribution from the top 5% of that red distribution. So alpha, right, or our 5%, is to the right of that critical value. Now, our alternative hypothesis of eta squared is equal to 0.073, right, with 40 total people, or 20 per group, leads to an expected distribution of F values that looks like this. So it looks a little bit better, but you can still see that most of this blue distribution is to the left of the F critical value, which means that our beta, or our chance of a false negative, is actually now about 59%. 59% of this distribution is still below the F critical value, so we actually now only have a 41% chance of detecting this difference, assuming that our assumptions about the effect size are correct. So it's a better situation, but if we have 20 people per group, or 40 people total, we're still only going to correctly conclude that men weigh more than women in about 41% of studies. So how many people do we need in order to reliably detect this difference? Well, reliable, right, depends on what you actually define your desired power to be. In many situations, we'll probably draw this cutoff at 80% power, where we want 80% of this distribution to the right of the F critical value and 20% of this distribution to the left. And without jumping through all of the different numbers, we can skip straight there and show that you actually need an n of about 52 people per group in order to have 80% statistical power, right? And again, we can show this by contrasting our null distribution against our estimated alternative distribution. And we make these two assumptions in order to calculate statistical power. So here's our null distribution again, and in this case, this would be an F with 1 and 103 degrees of freedom, because at 52 people per group, that's 104 total, minus the one additional parameter, right? So here's that F distribution. We get an F critical value of 3.93, which separates the bottom 95% of the red distribution from the top 5%, right? Because our alpha is at 0.05. And any value greater than 3.393, right? So any F observed greater than 3.93, we would conclude is statistically interesting and reject the null hypothesis. So what are the odds, what's the probability of getting an F observed value greater than 3.93? Well, given our eta squared of 0.073, right, and our sample size, we get an alternative distribution that looks like this. So you can see now our situation is much better. Most of this alternative distribution is beyond the critical value, right? So we have a good mass of this distribution to the right-hand side of the critical value, and only about 19% of it is to the left. So we have about a 19% chance of missing an effect that is there, assuming the true effect is 0.073. And the flip side of that is that we have about an 81% chance of correctly detecting an effect that is there, assuming a true effect size of 0.073. So if we have 52 people per group, we can correctly conclude that men weigh more than women in about 81% of studies. So this is in some ways a bleak scenario, right? Because we might assume that men weighing more than women is a pretty obvious thing to want to test. And if you think the effect you're trying to ascertain is more subtle than the fact that men weigh more than women, you probably want more than 50 people per group. And that can be a lot depending on what population you're working with and what your resources are. But fortunately, there are other things we can do besides increasing N to improve statistical power. I think that increasing sample size is very important because in terms of the precision of estimation and reducing variability from sample to sample, the larger we can make our sample sizes, the better. And in general, I think a lot of scientific research suffers from having too small of a sample size. However, right, there are other things you can do. So you don't have to just always think that I have to pump more people into my study. There are other things that you can do to increase your statistical power. The first is you can justify your alpha, right? So if you're replicating a well-established effect, or maybe if the cost of a false positive is really low, could your alpha be 10% instead of 5%? Right? If you're working in a life or death situation, maybe you want to be very cautious about concluding an effect is there when it really isn't, because that could have substantial negative outcomes, right? But if you're doing maybe more exploratory work, getting things started in a line of research, what is the actual cost of that false positive? And if you reckon that the cost of the false positive is really quite low, maybe you could make a case for a higher alpha, which would allow you to do an initial study with fewer people. Further, you can reduce the variability or the error in your data. For instance, by stratifying your sample, right? So to recruit a very specific subset of people, or through the proper use of covariates in your regression models, you might be able to reduce some unwanted error or variability, which is going to improve your signal-to-noise ratio in your data and proportionally make your effect size stronger, because now whatever the underlying effect was is bigger relative to the variability. If you can do things to clean up the error, proportionally now the effect size is stronger and should be easier to measure. Similarly, in some situations, you might be able to increase the size of the effect as the experimenter. Like in naturalistic studies, this is hard to do because that effect size is out in nature and you're trying to measure it. But in an experimental study, you might be able to make a choice about what kind of manipulation you're going to use. So for instance, in a drug trial, do I want to use a subtle dose of a drug or do I want to use a substantial dose of a drug? And if sort of risk of side effects and negative health outcomes are equal, I probably want to use the biggest dose that I can to improve my effect size. Or if I'm running like an exercise intervention, do I want people to exercise 30 minutes per week, 3 times a week? Or do I want them to exercise an hour a day for 5 days per week, right? And if I can do more exercise, I expect to see a bigger effect of exercise. So we can't always have direct control over the effect that we're trying to measure, but in those situations when we can, really trying to increase the size of our effect is another way that we can improve our statistical power without having to recruit quite as many people into our sample and making our study maybe a bit more logistically feasible.